Okay, welcome everybody. It's a pleasure to introduce Balint Virag that will introduce us to random plane geometry.
Thank you very much. Thank you for the invitation. So, yes, I'm going to talk about random plane geometry. This is kind of a provocative title, so I apologize for that. There have been many, I think in probability we have been searching for this kind of thing, which is what is the right way to think about random geometry in the plane, and there are many candidates, and I think somehow now we've sort of found the real thing. This is the real thing, in the sense that it's something that appears in many places, and we'll see it more and more now that we understand it better, and also it's very nice and kind of consistent theory mathematically. So, so what do I talk about? Well, here is a very simple model. You take a grid, right, and you assign edge length 1 or 2 or 1 or 3 at random, and then you see what distance you get this way and on this grid. So here, what I drew was a geodesic between the two opposing points in this grid. This is kind of what it looks like, and this is what the graph looks like. So this is the kind of objects we try to understand, and pretty much anything about this model is an open problem, but we still have a very good idea of what's going to happen once we can prove things, and again, so here it is. You just do this geodesics. Oh, there you go. Okay, so on z squared, and so you look at the distance. How far? What is the standard deviation distance? Standard deviation of the distance when you get some given Euclidean distance away, or given original graph distance away, and what you find empirically is that you have to go about distance sigma squared away, sigma cubed away to get standard deviation sigma. And when you look at the distribution of the distance, it doesn't look Gaussian. And the geodesics, when you look at them, see there you go about sigma cubed away. And the geodesics sort of go about sigma squared away from the straight line. So here is a simulation that my colleague did. These are some shortest paths that are drawn on the left, and on the right you see the distribution, and you can clearly see that this is a little bit too skewed already to be Gaussian. So what do we expect as sigma goes to infinity? Well, one thing is that because you don't have a Gaussian and because you have some strange scaling, there has to be some structure, right? Because we know enough in probability that if there is no structure, then you have to see some kind of trivial thing like Gaussian or Poisson or something like that. We wouldn't expect anything strange like this happening unless there is some internal structure. And the structure, of course, has to come from the geometry. So there is some kind of interplay between the geometry and the randomness that gives you something like this. So what do we expect? Well, here is kind of what we expect. So if I give you a direction v0, right, then you can find two vectors. One of them is parallel to this v0, and the other one is another vector not parallel to v0, and the scalar. So that if you so your v0 is going to be v is going to be your main direction in which you go about sigma cubed away, and u is going to be some kind of transversal direction. That if you do this kind of scaling, so scale with sigma cubed in the direction of v and sigma squared in the direction of u, and these things comes from the observation that I made in the previous slide, then the distance in this random geometry is going to be something like sigma cubed times the difference in the main direction, times some mean term m. So m is a scalar, right? So that's the main asymptotics. So this is kind of law of large numbers type asymptotics. But then we expect some kind of noise there. Okay, and the noise is depends on these 4 parameters, right? X, S, Y, and T, which live in the plane. So the noise itself, this is the nice part. You could think of it already as a geometry on the plane. Okay, so the actual discrete geometry here is roughly like some mean term plus some noise, which itself is a geometry. Okay? So this geometry is called the directed landscape. It was constructed 2 years ago, and it's some kind of universal random plane geometry. And I'm going to talk about a little bit of what this looks like, and also how this came about. So that's what this talk is about. So this is the asymptotics that we expect. Okay. So there is a minus sign here, as you see before the L, which is funny. So that's just because traditionally we didn't look at distances, but we looked at last passage percolation, where instead of trying to get there fast, you wanted to collect many cookies along the way. So that's a change of sign in the story, and so that's why the minus sign. There is this 1, 2, 3 scaling, as you see, right? You see here all of those numbers. Let's see what happened to my pen. I think I put my pen away. Okay. So you see 1, 2, and 3 in the scaling here. There is a 1 here, there is a 2 here, and there is a 3 here. 3 also there. And let me see, did I do this correctly? Yes. And this 1, 2, 3 scaling refers to this Carter-Parisi-Zhang universality class, which is Carter-Parisi-Zhang is basically the story of this random geometry in physics. So that's a paper from 1982, and everything around that is roughly about this. And now, another thing that you notice is that if you look in different directions, so if you change your V0, their main direction, then you have independent limits. Okay, so different directions don't really interact. In a given direction, your random geometry is a little bit skewed, and that's just the nature of this world. Okay. One nice thing about this L, which just follows from this asymptotics, by the way, is that it has to satisfy the triangle inequality. If you try to write this asymptotics, you know, the little o term of course cancels, and the other term also cancels. This mean term cancels. So automatically you will see that this L satisfies the triangle inequality, and so you think about it as a random metric on the plane where xs and yt are the coordinates of the 2 points. So that's what the directed landscape is, and this talk is about how this thing works. So again, what we expect is universality, like in the central limit theorem, that in many settings you will have this object, the directed landscape, appear, and it should always hold, no matter what the specific model you're looking at, right? So let's make that a little bit more precise. What is it that should not matter? So first of all, the distribution of edge lengths shouldn't matter, as long as they don't have heavy tails and things like this. If they're independent, you should get kind of the same answer. It also shouldn't matter that you're in a discrete model, right? That we looked at z squared, and we could have done something on r squared. We put some random Riemannian geometry on the plane by putting down, along Poisson, say a Poisson process, you would put some Riemannian metric. You would expect the same kind of behavior. It also shouldn't matter that this thing, and this is kind of interesting, I don't know why this is true a priori, but it is actually true. Whether you look at directed distances or undirected distances. So you could direct your grid in some direction, say northeast, and you would still expect the same behavior. I guess one reason for that is because this limiting metric, this directed landscape, is automatically a directed metric. So somehow in this limit, even undirected things become directed. So you can start with directed things and you get the same thing. Now, once you look at directed models, it shouldn't matter whether you look at shortest or longest path. Okay, so you may want to pick up, instead of looking at distances, you may want to pick up as many cookies as possible along path in a given direction. And that's, of course, last passage percolation. And you expect the same behavior for that. And finally, one thing that also shouldn't matter is whether you look at the absolute longest path or you look over some kind of exponential average of path, right? So you exponentiate the length and you sum overall path, and then you get this average. This is what you call polymer models, and you expect the same kind of behavior of polymer models on the long in the scaling. Okay, so this is why the kind of universality that we expect.
When you say what should not matter, you mean all of these things are currently conjectures?
So most of these things are conjectures. Yeah, there are a few theorems, and I'll tell them to you about later. Yeah. In fact, yeah. So essentially, the only so to this precision, the only things that have been proved are last passage percolation models. Okay, there's polymers proved almost to this precision, but I'll tell you about that a little bit later. Okay, so what should matter is that you're in 2 dimensions. So that's one thing, and then the other thing is that you shouldn't have heavy tails, and this actually seems to be a serious issue here. So it seems like you need 5 moments for this kind of thing to work. That's kind of the expectation. Again, there isn't very much rigor in this, but if you think about it, this actually may be quite a large obstacle for real life things. It's, like for CLT, you need 2 moments. Well, okay, you find that in real life. 5 moments finding in real life, not that easy. So you expect some other set of models also, which will have fewer moments and behave slightly differently, and you will see them in real life. But we're at the very beginning of this story, so we're just happy to have this one. Okay. And the other thing that is just like in ordinary plane geometry, right? There are many things which you can understand geometrically, even though they're not explicitly geometric. Right? So I call this hidden geometry, and there are a lot of hidden geometry in probability as well, including in particle systems. TASEP, I may talk about that. So that's essentially, again, this model hidden. There is like surface growth, right? In one-dimensional surfaces that grow, or interface growth. Tetris. There is, the most standard model of infection, the Eden model, which, by the way, one of my mathematical friends, who is not a probabilist, just said, oh, well, because of COVID, I started playing around with things, and have you ever seen this? And so he showed me the Eden model. It was quite funny. Then you can do 2-dimensional random Schrödinger operators. That world also. So it's a parabolic Anderson model and so on. You expect that kind of thing there. Longest increasing subsequencing permutations, you will see. I'll talk about that. And I think the most exciting one is really random matrices. And the connection there, I would say, is still only partially understood. It's one of the things that I'm really interested in how you would see. And so here's a picture of how you would walk from Thebes to Athens. Thebes is one of the ancient sites of the Pythagorean school. And then there is Athens. So it takes you 14 hours, and you see it's kind of like a geodesic in the random geometry, which is formed by nature and humans over the years. Okay, so here we're gonna do a little exercise. Okay, so we want to do, so this is the directed landscape. This is how it should be scaling, right? So let's apply the same kind of scaling to just ordinary Euclidean distance. Okay, so we have a Euclidean geometry, not a random geometry. See what happens when you do the same scaling, right? So this is symptotics. If you write it in the limit form, you get this. So basically, of Euclidean geometry, you get something like a norm. Okay, and so what does this norm have? Well, it looks like this. Actually, the norm is, so the norm of a vector ys is just y squared over s. You see how it's asymmetric. There's one direction, And it is that if S is 0. So you can see that Euclidean geometry in the scaling becomes directed. It means you can only go in one direction, in the time direction of the plane. And in the spatial direction, you can go in any direction. So geodesics will be, for example, graphs of functions in this direction. Okay. And there is no symmetry of this norm. So if you take minus the vector, it will not be the same vector. Otherwise, everything is fine. It satisfies the triangle inequality, just as you expect. And you can also define geodesics. They're going to be straight lines in this case. And so this is kind of a relaxation of the idea of a metric. You get a metric from this norm, where basically you give up everything except the triangle inequality and the fact that the distance from yourself is 0. But already when you have those two properties, a metric can be quite interesting. Okay, if you look at circles, for example, in this metrics, they become parabolas, and the center is actually the tip of the parabola. So the center is on the boundary. Okay, so what's the directed landscape at first shot? Well, it was constructed, by Duncan Dovern, Janusz Shortman, and myself in 2018, and it's a planar geometry. It's a random directed metric, and at the first order, if you like, it looks like this Euclidean stretched Euclidean norm, the one that I showed you in the previous slide, and plus there is some fluctuations. And the fluctuations, the magnitude just depends on the time. And the distribution doesn't depend on anything apart from the magnitude. It's always a Tracy-Widom distribution. And this is how it scales. Of course, those Tracy-Widom distributions are coupled in some intricate way over this L. So it's really a 4-parameter process. You can think of it as a function from R to the 4 to the real numbers. When S and T are in the wrong order, then you get minus infinity in this case. So otherwise, it's a finite number. There is no problems of regularity. It's a nice continuous function, okay, and satisfying the triangle inequality. You see, it's Tracy-Widom distribution, and it has a random fractal structure. So which comes from the fact that it's a scaling limit. So because it's a scaling limit, it's scale invariant. It's scale invariant under the scaling that you got this limit from. And it's, again, you see the 1, 2, 3 scaling. So if you rescale the points xs in a way indicated here with exponent 2 and 3, then you get this process level scaling equation. So it's very simple. It's a 1, 2 scale to 3 scale invariant random metric in the plane. So in order to understand this L better, it actually suffices to understand it for 2 fixed times. Okay, so there's a time direction S and T, and we're going to set S to be 0 and T to be 1, and want to understand these distances between 2 lines on these 2 specific times. Okay, so these fixed times specify 2 parallel lines, and we understand the distances there. And basically everything else can be put together from that using the fractal structure and independence, just like you put together Brownian motion from normal distributions in Lebesgue construction. So this is the thing to understand. The rest of it you can get from scaling. There's some work involved, of course, but this is what I like to focus on. Okay, so this Lxy, it's now a 2-parameter function, and I want to tell you where this thing comes from. So here is what Lxy looks like, by the way, this 2-parameter function. You can see there was a parabola in the stretched Euclidean metric, and you can see on the left the shape of the parabola. So when you go down on the parabola, that means x and y gets far away from each other. And when you go on the ridge of the parabola, that means x and y are the same and just changing. And you can see the carpet on the right-hand side is just a contour plot of the same thing. It essentially looks like locally at most places like the sum of a Brownian motion in x and the Brownian motion in y. If I got this correctly, yes. So it looks very simple locally. in fact, you could compute the Hausdorff dimensions of these curves, for example, that you see on the right. Okay, so here's now a theorem, just so that you see one. So the directed landscape is the limit of last passage percolation in many settings, geometric, exponential, Brownian, and so on. So these are now theorems. Directed first passage percolation, there's some versions of last passage percolation which can be understood that way. I will talk about that. Also TASAP, and I will talk about more precisely what that means. And longest increasing subsequences, I'll also talk about what that means more precisely. So this is now theorems in this world. So next question is what are these longest increasing subsequences are, and you probably all heard about it. So I just do a recap. It comes from this problem of Ulam in the 60s. How does the length of a longest increasing subsequence in a random permutation behave? So for example, here is the random permutations of numbers 1 to 6 to 1, 4, 5, 6, 3, 5. It has a bunch of longest increasing subsequences of length 3. We pick one of them, which is 1, 4, 6. Okay, and so for here, for this n, you get something which is of length 3. So the question is, what is it for large n? So Hammersley realized that this is the best way to think about it is geometrically. This is really a random geometry problem, and then Kingsman's ergodic theorem implies that that the limit exists. So I'll tell you what limit in a second. An interesting thing that the whole subadditive ergodic theory was essentially designed to work with problems like this. So that's where it comes from. So the limit would be, which I forgot to write, is that the length is roughly the length over square root of n should converge to a number. And finally, the constant in that, which I think is 2, was found by Loganov and Vershik and Kerov independently in 1977. So it's an old problem, and to get the fluctuations. So by the way, this is the main term. If you think about geometrically, this is the main term in our expansion, the square root of n, in this case. And the fluctuations at one fixed point were found by Bagdev and Johansson, quite a bit later, as you can see. So 22 years later, and they identified it as a trace-Subidom distribution. A few years later, Prehofer-Spohn have constructed a process which is this essentially this two-parameter function, but one parameter fixed. So you set one parameter to be 0, and you can move the other parameter, and they've constructed, this is called the Airy process, and I'll talk about later. And in 2018 we constructed the whole object. So here is what a random permutation looks like geometrically. This is one way to present it geometrically, right? Is that you have the permutation 2, 1, 4, 6, 3, 5, right? And you take a grid and represent it by making certain edges in the grid longer. Okay, so you see in the first column I made edge number 2 longer because of the first number 2. Then in the second column I made edge number 1 longer. And the third column I made edge number 4 longer, then 6, then 3, then 5. See that? Right. So this is sort of a geometric representation of this random permutation. And now what I'm looking for is the longest path, okay, from the bottom left corner to the top right corner. That corresponds to the longest increasing subsequence in the permutation. Okay, so it's very simple. If you don't believe me, think about it a little bit. And you see you have the permutation 1, 4, 6, the longest increasing subsequence 1, 4, 6, which corresponds to the long edges that I picked up, right? I picked up the long edges corresponding to 1 here, the long edge corresponding to 4, and the long edge corresponding to 6, right? So it's the longest path, longest directed, so upright path in this grid, and that picks me the longest increasing subsequence, right? So you already see how you can introduce parameters here, because when you do this longest path, you can move the starting point and the end point on the bottom and the top of this grid, right? And then this way you get automatically a 2-parameter process. And you hope that that 2-parameter process has a scaling limit, and it does, although it takes a little while to prove that. Okay, so that's what we're going to talk about. That's what I'm going to talk about. So here we're going to do what we're going to do exactly. What we're going to do is not a permutation. So we're going to pick these long edges not according to a permutation, but just independently. Okay, you can do it with an independent Bernoulli process. Again, only on horizontal edges. And then, by the way, this is not hard to relate after to the random permutation case. It's actually quite simple to do that. And for here, I actually picked Bernoulli with parameter 1/2, but you can make the parameter smaller. You can make it go to 0 with 10. You can do all kinds of things that will relate it more to random permutations. But let's just look at the IID model, where for each edge I flip, or each horizontal edge, I flip a fair coin and make it thick or thin according to the outcome of that coin. Okay, so all the long edges say they have length 1, and all the short edges and the vertical edges say have length 0. Okay, and so you can see here are the realization, and you see the longest path in this case, which is in this picture you see has length 5, right? And what you see up there is the data that this thing is built on. So the Bernoulli process that is there. So how do we understand this model? So this is a little bit of a longer slide. The understand is through the RSK correspondence. Okay, that's the main way. It's actually quite beautiful and simple. And I think I can explain it in 5 minutes here, if you haven't seen this before. So the one that I'm explaining now is just a version, okay, which is there are many versions of RSK now. This is one that will be nice for this process. Okay, so I have this. So what does RSK do? So I have kind of an n by infinity array of 0 1s. Okay. So n is 3 here, and infinity, well, is the other direction. And I'm going to assign some to this array, a bunch of functions, okay, or a bunch of, well, these are discrete functions, and those are represented on the right. So they're actually Bernoulli path, if you like. So what's happening? So the first path, W1 or Y, it's going to be a function of Y. It's just the distance of 0, 0. So that's the bottom left corner to yn, where n is fixed and y is changing, right? N is just my number of lines, and y is the location of where the endpoint of my path is going to be, and the distance is in terms of longest path, right? So that's what I mean by distance in this case. So W1 of y is just this, and what it is the top line, the blue line here, if you can see. So you can actually check, like if you go from here to here, time 1, the distance would be 1, because if you want to go here, you can pick up 1 cookie, right? Then again, to here, the distance will be 1, because there are those 2 cookies that you can reach, but you can't reach both at once, right? And if you go to here, you can already pick up 2 cookies, those 2 on the second line. So then you have jumped to 2, right? So you see that over here, and so on. So this top line sort of records how many cookies can you get if you start from here and end up at sort of y in the top line here. Okay, that's what the blue line is. And the next lines are defined very similarly, except you're allowed to now take not just one path, but k paths, okay? And you look at the union of them, and you can see how many cookies that picks up, okay? So that's what I call decay, okay? And then these w's are expressed, the sum of the w's are, first k w's are equal to this decay. What this is, by the way, if you're familiar with RSK, this is called Green theorem in RSK, but we can also just define RSK this way. So one fact is that these W's are going to be a non-increasing sequence of functions. So the picture that you see is actually always like this. So the blue line is on top, the orange one is weakly below, and the green one is weakly below the orange. So W1, W2, W3, and there is an amazing property, which is RSK is almost surely a bijection. Okay, I won't explain this anymore, but the main thing is just because it's almost surely a bijection, it should send uniform measure to uniform measure essentially. And so uniform measure on these arrays is well, that's just, Bernoulli processes, that's obvious. So what's uniform measure on the target? Well, we have these non-increasing set of paths. So what's uniform measure on them? Basically, they're non-intersecting random walks. Okay. So because it's a bijection, this is what you expect.
Balint, can I ask a question? So you have the union of k paths. Could you elaborate a little bit? Why not take all of them to be the same path? Is there any restriction?
Because you don't count things twice. That's why.
Okay. So you first take the union and then you ask how many ones did that union contain.
Good question. Yeah.
Yeah, and still these are paths that go only right and up.
Yes, that's right.
Perfect. Thanks.
Okay. So this is one thing. So RSK on the one hand is a bijection, which is of course beautiful for a probabilist because it maps nice measures to nice measures. And in fact, you can put some weights in that thing, and you can get quite a bit more out of it than just uniform measure going to uniform measure. But this is sort of the basic idea. And again, we map Bernoulli processes to non-intersecting random walks, which is the uniform measure on the possible configurations on the right. Okay. And for this, by the way, you have to take n by infinity arrays. If you take finite arrays, there's still something like this, but it's a little bit more complicated. Okay, so another thing that RSK does, which is quite amazing, is that it's an isometry. So it preserves distances, and that's kind of something that I think it was first exploited in our paper, essentially, although it has been known in various cases in various ways. But not really well. So once you have this image of your RSK bijection, you can define a metric there, okay? And you would think of this metric again as with having two parameters. So x is a point on the bottom line and y is a point on the top line, okay? And so what is this metric? So it's basically what you do is you start. Let me see if you can see what I'm doing. So you start here in the bottom. Okay, let's try that. And you have some kind of path. You start on the green path for a while. You pick up some increments of the green path. Then you jump to the orange path. You pick up some increments of that. And you jump to the blue path and pick up some increments of that. And you sum these increments and you optimize over all ways of jumping. Okay. So this is what this DW is. This is the RSK metric. Okay. And the amazing thing is that that for all x and y, okay, you have an isometry. So the last passage metric that we had before, from the bottom line to the top line, it's important, this is only true there, is equal to the RSK metric between those points x and y. Right? So this is an isometry, which is extremely useful. Okay? So it's a bijection and an isometry, fantastic for proving things in geometry for us. So that's what we do. By the way, when x equals 0, this is essentially true by definition. But when x is not 0, it's kind of a miraculous thing, miraculous property of RSK. It's true for all x, not just for 0. Okay. So this is kind of enough for me to tell you how you take limits, essentially, because everything else is something you will believe, right? So now we'll do scaling. Okay. We let scaling go to infinity. So what happens to the non-intersecting walks? Well, they become non-intersecting Brownian motions, and there are infinitely many of them. Well, we've taken that scaling. So sure, and that thing is called the area line ensemble. There are just infinitely many Brownian motion condition not to intersect. Okay, this thing makes perfect sense. I'm not going to say much more about what it looks like, but it does make sense. The reason that this can make sense is because in the scaling, these things kind of become like parabolas, and so when you make them non-intersect, they sort of stretched on top of each other, and there is a top line, and the whole definition is perfectly consistent. And the RSK metric, right, that I discussed just in the previous slides becomes kind of a metric along this area line ensemble. So you have to do this kind of path metrics along here, just like before. Now, there is one thing which is a little bit more subtle, which is that there is no bottom line, okay, in these Brownian motions. There are infinitely many, so you can't start anywhere. So to define the ALE metric, area line ensemble metric, you have to take limits. So you go in a certain asymptotic direction, you look at the distances and normalize, and so you can think of it as some kind of Boozman functions or horocyclic distance in this world. So you have to look at a limiting metric from infinity from a certain direction. Okay, so the area line ensemble distance is defined this way. From xy is a limit of this kind of path metrics that I described before, from a point xk to y minus ck, and this point xk to y is going to infinity in this specific way. So on the kth line, you're going to start from minus square root of k over 2x, and you take what is the distance from that point, and then you take a limit, and you get like that. So that's a short summary of what we do in our paper about the directed landscape. It takes a little while to prove that these things exist and so on, and also that we converge, but we do, and in this way we got the geometry, okay, that is constructed based on this area line ensemble. So LXY is just actually defined as this area line ensemble metric. Okay. So how does, let's just say some remarks about the proof. So you know, this is something that you've probably all seen. So non-intersecting walks are expressed as determinants using Carlin-McGregor or Gesell-Viennot formulas. And then these determinants, there are many ways, after you have these determinants, there are many ways to go. One way is to write them in terms of orthogonal polynomials. And then you take limits of these determinants with orthogonal polynomials in them. The orthogonal polynomials, almost all of them, if you look at near the edge, they become kind of Airy functions. This is a standard fact in the theory of orthogonal polynomials. And that's why in the limiting formulas, you have all those Airy functions coming up. And that's why these processes are called Airy processes. And then there is a beautiful idea of Corwin and Hammond, which is that there is a nice Gibbs sampling property of the non-intersecting walks, and that Gibbs sampling property lives in the limits, and it makes this area line ensemble very easy to work with. So when you resample things, you can see the Brownian structure in the limit. Let's say that way. Okay, so we have constructed this directed landscape. Let's say some things about it. So one thing is that you can define geodesics in it, okay? Because you can define a path, you can define the length of path by subdivision, just like in any metric space. And the geodesic, so I defined as the shortest or longest path, depending on the sign. And there is another interesting thing, that there is essentially only one geodesic, because the two endpoints. Of course, there are geodesics between two endpoints, but these two endpoints you can move by affine maps, and there is some kind of affine scaling invariance of this limit. So there is kind of a universal geodesic there. If you have two fixed points, then with probability 1, there is only one geodesic between those two fixed points, although there are special points where there are more than one geodesics. Okay, and so here is a picture, by the way, of what this geodesic looked like in the directed landscape. On the left-hand side, maybe I shouldn't say, sometimes I do this as a riddle. So the left-hand side is a directed geodesic. On the right-hand side is a Brownian bridge. So there, as you can see, the left is kind of a little bit more regular on the small scale and a little bit less regular on the large scale. And it is a scalar invariant process. It's essentially, and it's further continuous with exponents 2/3 minus. Okay, so it's more continuous than the Brownian bridge, and Duncan will have a lot more to say about this in his talk. And here is our theorem about the longest increasing subsequence, about its shape, right? So the Baghdad-Johansson paper result is about the length of it, but we now look at the shape. So you take this sequence, I don't know, 1, 4, 6 that we had, and now they're about one that is about two square root of n long, and you plot this sequence in Mathematica, right? You get something which is close to a straight line. Now you subtract the straight line, and you get some kind of fluctuating curve, right? Which is just the sequence itself. And this curve, okay, Ln, we call that, well, the longest increasing subsequence I call Ln. And you see the main term is this n times t, so it's roughly a straight line, plus there is an n to the 1/3 times there is this gamma of t, and gamma of t is actually the directed geodesic in the landscape. So the longest increasing subsequence has exactly the same shape as the directed geodesic in this random geometry. Okay, so that's the story of the longest increasing subsequence, but there are other worlds where this geometry appears. There are many hidden geometries. So one of them is...
Can I ask a question?
Yes, of course.
In case you don't have uniqueness of the discrete geodesic, do you get something about the correlation of the two possible geodesics, like the 2-point function of the of L?
Yes. So right. So in Ln there is no uniqueness, right? There are actually stretched exponentially many geodesics, but the interesting thing is that all geodesics converge to the same limit. Okay, so if you look at the difference in, say, in a supernorm of two geodesics, that converges in probability to 0 in this scaling. Does this answer your question?
Well, you can also look at convergence together, and this might have a more interesting structure.
Right. So you could look at convergence together, and you can look at the rate of the convergence and these kind of things. So those are more refined questions. But in this scaling, all you see is that these geodesics, they go to the same limit. So this kind of non-uniqueness is a local phenomenon. Right?
Thanks.
It doesn't exist in the scaling. But just to iterate once more, if you allow to vary the endpoints, okay, then there'll be in the directed landscape, there are points in between. There are more than two geodesics, and the best upper bound we have is 9. So we know that between any 2 points in the directed landscape, there are at most 9 geodesics. Where we can prove that there are points in between which there are 4 geodesics, but we cannot go above 4. The upper bound is 9. So there is this kind of questions. Okay, so there is longest increasing subsequence, and well, you know, there are polymers. I sort of explained what those are, and then there is a KPZ equation, which I'm going to say a few words. And there is a TASAP, which is a particle system. I'll talk about it. That actually comes from biology. TASAP was introduced in a biology paper before mathematicians cared about it. Random matrices, which is a huge. So if you look at Hermitian Brownian motions, so a random matrix filled with Brownian motions, then its top eigenvalue behaves like this Airy process. But we're not aware of any random matrix model in which you have these 2 parameter processes appearing, L of xy, and that would be really, really nice to find something like that. We don't quite understand the extent of this connection. And then there is Tetris. So what we expect from Tetris, we can also define a geometry in terms of Tetris where people don't play. It's just Tetris with stuff falling from the sky. You see a surface growing, and the fluctuations of that surface should be described by the random geometry here. Okay, so I want to talk a little bit about the KPZ equation. Right, so now again we're looking at something directed on the graph. You have edge weights, and instead of looking at shortest path, you're looking at exponential averages over all path. Right, so this is exponentiate the length, and you average over all path, and you take a log. So if you fix the starting point of the path, then this distance as a function of the endpoint satisfies a difference equation. Okay, it's easy to figure out, right? It's just how it changes when you add a little bit of randomness, right? And it's a difference equation in 2 dimensions, right? Because the endpoint lives in 2 dimensions, and you can take a continuum limit of that, and you get the stochastic PDE. Okay, and essentially this is what the Carter-Perez-Zhang equation is. This was introduced in physics in 1982, and the whole universality class was named after them. So HT of X is essentially a solution of the PD, which is the limit of what this difference equations would be in the discrete case. And in fact, you can also associate, as was done by Albert-Kanin and Castell, a continuum directed polymer model to KP, which is essentially you take the graphs of Brownian motions and you weight the path by white noise, right? And so that's kind of a probabilistic interpretation of KPZ, and this is what the equation is, right? And you can kind of make sense out of it. There are many ways to do it. If you do it really well, you get the Fields medal, and that's what Martin did. Quite. Of course, he did much more, but this is a sense of he did, and so there is one result which I did during COVID. Essentially, what was known about this is that if you fix one point, then that converges to Tracy-Widom, so like a single point. And now I know a little bit more. So if you look at this KPZ equation, its solution essentially looks like something in the directed landscape. So here is the asymptotics that is precise here. So if you start with some delta initial conditions, then you can write the solution, the limit of the solution in terms of the directed landscape. And you can also generalize this to, this actually works for more general initial conditions, just a little bit longer to write. So I didn't. So there is, this is kind of a new result I'm a little bit proud of because this is like the equation that gave the name to the whole area. And there's another proof which happened quite amazingly the same time and the same place. Here in Toronto, we worked kind of independently of each other and we didn't know, which is quite amazing because like Surav, who is the other part of Castell Sarkar, he was working with me on other things. And there is a completely different proof of this, which is generalizable in different directions by Jeremy Castell and Surav Sarkar. So this area just being kind of stuck for a long time because the exactly solvable ways that this was treated before just basically got stuck at the point. Now there are various ways to proceed. So there's hopes for things. And finally, maybe I'll just say quickly the TASAP, right? So you have the particles on Z on a site and at most one per site. They iterate one jump to the right. So this actually, I think people study ribosomes in cell biology. I'll say a little bit about this in my last slide. It's a model for them. They actually use this to understand those things. It's not just some kind of useless math that people pretend to be useful. This is actually used in biology to understand ribosomes. And the height function of it turns out that this height function of the TASAP, which I drew here, which is basically the integrated, if you put zeros and ones according to the particles and holes and integrate, you get this kind of height function. And this height function turns out to be exactly a circle in a certain geometry. And the geometry is directed exponential last passage in that square. Okay, so it's a boundary of a ball. The scaling limit of this was proved by Matetsky, Costello, and Remenek in 2016. It's called the KPZ fixed point. And we have a representation of this in terms of the directed landscape. It's just, so L is the directed landscape. As you see, it's an extremely simple variational formula. So at time t, the Tay-Sep limit looks like at location y, looks like you just take sort of maximizing the distance from some initial condition h0 of x with respect to this random geometry. So there is hidden geometry, but very, very simple and explicit here. And what we proved is that this thing actually holds jointly over all initial conditions, which is something that the old methods cannot prove. And one thing that this is good for is understanding second-class particles. Okay, and so I'll finish now. Here is I don't know, you probably have heard mRNA nowadays, right? It's something that nobody really heard until now because of the vaccines. But yeah, so this ribosome is this gadget that goes along the mRNA and makes proteins. And what happens with these ribosomes is that they have traffic jams, right? Because they go along the way and they bump into each other. And those traffic jams are modeled by Tay-Sep. So maybe I'll stop with that and open up for questions. Thank you.
Thank you, speaker. Questions?
Yes.
Balint, if possible, can I ask a question?
Yes. Where are you?
Is there a way to embed the corner process in random matrices into your two-point geodesic? So if you take the Brownian motion matrix, you get a marginal, which is airy.
Yes.
And what happens if you look at the short answer is no? Yes,
you get a different thing.
Okay, and what do you get?
A different thing. So there is another two-parameter process whose marginals are airy processes, all kind of ways, which is the limit of what you're asking. But it's not the same. So one of the things that is always telling, I should show you this. So this LXY that I told you, right? It comes from geometry. Maybe I should show. I can. Let me see if I can do this. Just 1 second. Okay. Let me see if I can do a screen sharing here with something else. Okay, can you see this?
Yeah.
Okay, so here's what happens, right? So you have two lines, and x is moving on this point, and y is moving on that point, right? And you have these 2 points, and what you describe is their distances. So here is an interesting thing. If you take 2 points on the top and 2 points on the bottom, right, then they kind of give you a quadrangle. And you have diagonals on the quadrangle. And you know from Euclidean geometry that the sum of the diagonals of a quadrangle are longer than the sides, some of the right and left sides of the quadrangle. That's just two triangle inequalities put together, right? So there is an analogy of this here, okay, with the other inequality because of the sign change. And that tells you that this airy process doesn't have full support. Okay, so if you look at x, y, if you 2 values of x and 2 values of y, then they're not supported on the entire R to the 4. And all these other processes with the corners, they are supported everywhere. So these are sort of genuinely different.
Okay.
Balint,
Yep.
you mentioned also in the beginning 2D random Schrödinger operators. Yes. Can you say something about that? About the connection?
Yes. So I think okay, so the 2D Schrödinger operators have, you can think of them as generators of a polymer model, okay, which is a generally two-dimensional polymer model. Right? There is no direction, and in this sense, it's because polymers can be thought of distances in some sense. If you take the logs the right way, you'll have a two-dimensional geometry there. And the two-dimensional geometry, if you look in the right directions, have a scaling limit given by this Dirac landscape. That's a conjecture.
Mhm.
At the moment.
All right. Okay, thanks a lot.
Oh, hi. May I ask a question?
Yes.
So, beautiful talk. Thank you. Now, you discussed, your focus was on the continuum limit, but I wanted to ask whether the methods which are now at your disposal allow to settle an old conjecture about the lattice model, which is that if you look at the random geometry on a lattice, then with probability 1, there is no double infinite geodesics.
Oh, okay. So I think, right. So I think in the models that we can take limits of at the moment, I think this thing has already been settled. If I know, I haven't worked on this, so I'm not. So this directed last passage, integrable directed last passage model, these things are well understood, that they don't exist. I can give you something which is positive in this direction, which is that in the limit, and Duncan will talk about this, you can actually construct these doubly infinite geodesics, and they're relevant because that's what, if you look at a usual geodesic, right, and you look at kind of an internal point, and you took a scaling limit, so you zoom in around an internal point, you see a doubly infinite geodesic. So if you want to understand what these usual geodesics look like, you sort of have to construct that object. And so we did that. We did construct that object with Duncan and Surav.
Yeah. The two statements, of course, are consistent with each other, yes, because the density of such points is 0.
It's not
measure.
That's right. It's not only that, they don't even exist. So in the limit, those points don't exist. You have to force
but
them.
In the continuum do exist, but not on the lattice, I guess.
In the continuum, they don't exist either.
Oh, that's right. That's right. Yeah, of course. Yes.
So you have to force them.
In a finite volume, you do have, but not the infinite. Yes.
Mm-hmm.
Thank you.
The way they exist is like you have to do a scaling limit of a fixed geodesic, and only in the limit will you see this object.
Right. So if you take a square and take the continuum limit, and then look at the collection of geodesics which link 2 points on the boundary of the square, and take the next infinite volume limit, then the geodesic paths probably would no longer visit the center core of that square.
Yes. It will leave your window. Yeah, you won't see them.
Yes.
That's right. That's right. So you have to move your window to be on them. And
yes.
Then you can do that. That's fine. You can do that, and it makes sense. And there is a limit. Yeah.
Okay, so let's thank Balint again.
Sorry.
Oh yeah, one last question.
Yeah, can I ask another question?
Yes.
So,
a couple.
In this, at a certain point, this RSK, and my question is: do you expect that this directed landscape is, in some sense, also related to standard Young diagram, and should appear somewhere also in this model?
It's more than that. I mean, it's essentially that. I mean, these are Young diagrams. I just didn't use that language.
Yeah, exactly. Okay.
Yeah, so absolutely. Yeah.
Okay. And another,
I could say the analogies of what I said exactly in that language. I just try to avoid it because it takes a little bit longer to explain.
Okay. And another more question related to your title. So there are many other models of random geometry, and obviously it comes in my mind the Liouville quantum gravity.
Yes.
And so in my mind, they are really two orthogonal models, but do you expect some relations or some way to connect them, or they are two different models? That's it.
No, I do expect, yes. So,
Okay.
so there should be directions in which if you take the Liouville quantum gravity, you'll get this as a limit.
Okay.
But not,
But-
I think the other way around. But this is kind of, you know, it should be a scaling limit of certain directions of Liouville quantum gravity.
Okay, but
And yeah, go on.
yeah, does your metric have some conformal properties, something like that? Because
Yeah, so
this
you
is
have to
a
go in a
really
way
big.
that the conformal invariance vanishes, right? So if, for example, if you go in a very long direction, and then and you scale in an uneven way, right? Then you won't see conformal invariance anymore. And so that's the limit that you expect these things to show.
Okay, very nice. Thank you.
Okay.
Thank you.
Thank you. Do you want to unshare so the second speaker can share his screen?